today's video, we're going to be talking about the different types of forces that you'll be seeing in this class. After watching this video, you should be able to understand the different types of forces and be able to draw something called a free body diagram. I really like these things. They really help you see what's actually happening in a problem. So being able to draw a free body diagram, to me anyway, is really important. And then after you've drawn a free body diagram, you should be able to calculate the net force on an object by using that free body diagram that you just drew. Okay, so let's get right into it. So something that kind of came to me was, hey, we haven't even defined what a force actually is. And it's pretty simple here. You can see it just in one sentence. A force is a push or a pull on an object that interacts with another object. Okay, so a force is a push or a pull on an object that interacts with another object. All right, so that's all a force is. There's really two types of forces that we're going to see, and in the broad sense. Okay, I mean there's more than two types of forces, but in the broad sense there's something called a contact force. And as the name says, a contact force is a force that results when two objects are actually touching each other or physically contacting each other. And there's a whole bunch of those right here that I list. So the frictional force, tensional force, normal force, air resistance, applied force, I mean those are all contact forces. So basically it means you need to be in physical touch with another object. Okay, so these won't happen unless you're actually touching something. The other type of force is what I call an at a distance force. And basically that means that the two objects are interacting with each other, but they're not actually physically touching each other. And for first semester physics, the one example we're really going to see that happening is gravity. Okay, we all know that you could be, up in a plane, but the force of gravity is still acting on you, and even though the Earth isn't actually physically touching you. So gravity is like an at a distance force. In second semester physics, we'll look at like the electric force, and that's also an at a distance force. But we don't have to really worry about that right now. For right now, what we're mainly concerned with is this gravity piece. That is our at a distance force. So what is force measured in, or what is the unit of force? The unit of force is the Newton, okay, and that's usually signified with a N. Okay, so if you say like 5N, that means 5 newtons, and that's a force, okay? And what is a Newton? Well, 1 Newton is the amount of force required to give a 1 kilogram mass an acceleration of 1 meter per second squared. Okay, so a Newton of force will cause a 1 kilogram mass to accelerate 1 meter per second squared. That's what a Newton is. Okay, so anytime you see newtons, you're talking about force. Now, just like velocity and displacement, force is a vector quantity. Now, what does that mean? Well, that means it'll have a numerical value, so 5, and it will have a direction. So right here, I need to either put like a plus or a minus sign in front of this to indicate or what direction it's going, or you could just say like 5 newtons to the right, and that would be the directional piece. Okay, so now we know that 5 newtons to the right are acting upon an object. Okay, so it has a direction and a number value. So here's a big old list of the different types of forces that we're really going to be dealing with for first semester physics. Okay, there's something called the applied force, and this is abbreviated as FAP. And it's applied by another object. So, I mean, let's say you're in the hallway and you push someone. That's an applied force. You just applied a force on someone else. Let's say your car hits a tree. Well, you just applied a force onto the tree, or car did, I should say. Okay, so that's F applied. The force of gravity is basically the gravitational force, and that's what gives us weight. Okay, so when we say our weight, we're actually talking about how much gravity is pulling down on us. So my weight would be very different, say, on the moon or on Mars, because there's a different amount of gravity on those objects. Sometimes, and I will do this often, I won't actually write grav. I'll just write F sub g, and that's the force of gravity, and that's probably almost more typically what you will see. The normal force is kind of like a support force I talked about in the previous lesson, but basically like I'm sitting on a chair right now, so the chair is providing a normal force pushing against my weight. Okay, if the normal force wouldn't balance my weight out, I would fall to the floor right now. And a lot of times you will see this written as big F sub n. So that's normal force, and that's how I usually will write it too, because I just don't want to write norm. But you can, nothing wrong with doing that. The force of friction is a frictional force. Basically, it opposes motion, and it can be F sub fric if you want, or I like F sub F. I think that's easier. I'm all about writing less. So if you want to write that, that's great. Air resistance is basically friction from air, and that's F sub air. If you do F sub A, I probably will know what that means too, so that's fine also. The tensional force is a force that's provided by like a rope or a wire. So if we're like hanging a sign or something with a rope, there's tension in the rope or the wire, and that's the force of tension. So that's F sub tension, or 10, sorry, or sometimes people write F sub T. That's another way of saying it. And the spring force is the force from a compressed or stretched spring. Okay, so those are the types of forces that we're dealing with and looking at. So on that gravity piece, there is a misconception that people have. They think mass and weight are the same thing, and that's not true. They're actually two totally different things. They are related, but they are two different things. The mass of an object refers to the amount of matter that is contained by the object, whereas the weight of the object is actually the force of gravity acting upon that object. Okay, so when people say they want to lose weight, that's really not actually scientifically accurate. They really should be better off saying, I want to lose some mass, because your weight is actually dependent upon the force of gravity. Like really, if I wanted to lose weight, I could just go into outer space and I could like weigh almost nothing, right? And I lost weight. Well, what a great weight loss program. But really what I want to do is lose mass. So keep those two separate. They're not the same thing. So again, weight is dependent upon G, which remember G is the gravitational field strength, and on Earth, G is 9.8 meters per second squared. So here we go, we're getting into free body diagrams, and free body diagrams are basically used to show the magnitude and direction of all the forces acting upon an object. Typically free body diagrams, whatever the object is, whether it's a car, a squirrel, a human, you name it, it's typically represented with a box. Okay, so it's wonderful for those who are artistically challenged. I can draw an okay box. Okay, so you draw a box to start your free body diagram, and then you're going to put arrows on this box to show the directions of the forces that are happening to this box. And each arrow should be labeled, and I would label it with A, the direction. Okay, so the direction you draw the arrow gives the directional piece to the force, and B, label it with the numerical value. So if I am applying a force of 5 newtons to the right on this box, I would draw an arrow to the right, and I would label it 5 newtons. Okay, so I'm applying a force of 5 newtons to the right on this box, just so it's real easy to see. And usually the object is a box. Sometimes I'll see it even as like a dot, and then let's say I apply 5 newtons of force to this. That would be another way of doing it. The box is kind of nice because it allows for more space for you to draw things around it, whereas a dot, it can kind of get messy. So let's do some example problems of free body diagrams and see if you can identify what forces are acting upon these examples. So it says a book is at rest on a tabletop. Diagram the forces acting upon the book. Okay, that should be simple enough. So I'm going to draw a box. Okay, the box is the book. Okay, if the book's sitting on a tabletop, what forces are acting upon the book? Well, one way to do free body diagrams, at least how I recommend doing them, is just about everything is going to have weight, right? The force of gravity is going to be acting on it. So I'm going to write F sub G. Okay, then I ask myself, what is touching the book? What forces are touching, because basically all that's left is contact forces. So what is touching the book? Well, the table is. So what force is the table applying to the book? Well, that is called the normal force, F sub n, the normal force. And basically these two forces are balanced, and that's why the book is at rest, it's not moving. If the forces weren't balanced, the book would actually be moving. Forces cause a change in motion. Okay, so F sub G, F sub n, we're good. That's a free body diagram of this example. Let's do another one just to kind of get ourselves thinking more. A car is coasting to the right and slowing down. Neglect air resistance, diagram the forces acting upon the car. Well, again, the beautiful thing is I don't actually have to draw a car. I think you guys have seen some of my cars, and it is not pretty. So I just have to draw a box, and it says a car is coasting to the right and slowing down. Neglect air resistance, and then let's do this. Let's do a free body diagram. I recommend starting with weight always first, because everything will probably have weight unless stated otherwise. So to show weight, we're going to draw the force of gravity, F sub g. Okay, there it is. Now I ask myself, what is touching the car? Okay, and we know air is touching it, but it says neglect air resistance. Well, is the car on the ground? And the answer is, yeah, I think so. I don't believe this is a spaceship. So what is the ground doing to the car? Well, it's pushing it up, and we call that a normal force, F sub n. Okay, so that's two of the forces. There is one more. The car is slowing down. What would cause a car to slow down? Well, I'm thinking it is friction, right? And so the friction must be going to the left. You may say, well, how do you know that? The reason I know that is because it's coasting to the right and slowing down. So to cause it to slow down, it must be slowing it down to the left. A force must be being applied to the left and be slowing it down. Okay. Notice there is no force that's causing the car to move. Okay, it's coasting. So motion, it does not need a force to have that happen. Basically, a force causes a change in motion. Okay, so keep that in mind. I know it's a hard concept to wrap your mind, or at least it is for me, but keep that in mind. So here's a free body diagram of this scenario. Let's do one more. A football is moving upwards towards its peak after having been booted by the punter. Neglect air resistance and diagram the forces acting upon the football as it rises upwards towards its peak. Okay, so this is a weird looking football. It's a box. So this football has been punted. It's in the air. Let's look at the forces that would be acting on this guy. Okay, so the very first thing that you do always is do the weight, okay, or the force of gravity, right? And so the force of gravity is always going to be down, and that's supposed to be an F. I'm really sorry that came out so funny looking. F sub g, right? So the football is moving up towards its peak. The force of gravity is pulling it down. Now, what is touching the football right now? Well, you may say air, but it does say neglect air resistance, so we don't have to worry about that one. That's good. Is anything else touching the football besides air right now? And the answer is actually no, there isn't, right? And so this is actually it. This is the only force acting upon the football is gravity. And this actually is what's called free fall, okay? We talked about this in the previous chapter, where basically the only force acting on an object undergoing free fall is the force of gravity. And there it is, okay? So that's it. All right, now had we done this when like the foot of the punter was touching the ball and applying a force to actually cause the punt to happen, this would be a different picture. But right now it's saying the football is actually just in the air. So the only force acting upon the football in the air is the force of gravity. All right. The net force is the vector sum of all the forces that act upon an object. To calculate the net force, you must add up all the forces in the horizontal or vertical direction, or it could be in both. I mean, there could be forces acting in all the directions. And if there is a net force, an acceleration occurs, okay, which will lead us into some later lessons with this acceleration piece. Okay, so it's pretty simple. You just basically add things up and figure out what the net force is. So let's do some examples, because I think that's worth 1,000 words instead of me trying to explain it through text. I'm just going to look at situations A and let's see here. We'll do D. A and D, just so I keep these videos a little shorter. So here's a box, and you notice there are 4 forces acting on this box. Let's take a look at the forces in the vertical directions. Okay, so we have the force of gravity, and it's 3 newtons, and it's going down. And we have the normal force, and it's 3 newtons, and it's going up. Do these forces balance each other out, 3 newtons up and 3 newtons down? The answer is yes. So there is no vertical net force, if you will. Okay, they've been canceled out. Now what about in the horizontal direction? Well, there's 5 newtons of force being applied to the right, and there's 5 newtons of frictional force being applied to the left. Do these forces balance each other out? The answer is yes. So F net, or the net force acting upon this object, is 0. Okay, there is no net force acting upon this object. So there is no change in motion. It could be moving, it could be sitting still. We don't really know. It's just 0 for a net force. Let's take a look at situation D. In situation D, we have no forces in the horizontal direction, right? So we don't have to worry about anything with that. We do have some forces in the vertical direction. We have the force of air resistance, as 40 newtons and the force of gravity as 25 newtons. Is there a net force? Is there a difference between these two numbers? And the answer is yes. So basically, you just take 40 minus 25, and if you do that math, you should get 15 newtons. Now remember, a force is a vector, so we have to say a direction on this. What direction is the net force going? Well, the net force is 15 newtons up, and that would be my answer. All right, so that's basically it. That's kind of taking a look at free body diagrams and determining the net force on them. I will see you guys in the next video.